Okay, so this is going to be my first attempt at a little lecture video. This is on our first new topic. It's called calorimetry. Calorimetry basically means measuring calories. And in our case, measuring calories means you're measuring energy or energy changes, energy transfers. And generally that has to do with heat being transferred in or out of a system. A calorie is just a unit of energy, hence calorimetry, measuring calories. So calorimetry is used to calculate enthalpy changes, which are sort of like energy changes for physical and chemical processes. This term enthalpy, you can think of it essentially as potential chemical energy, stored energy within these substances, within these molecules. And enthalpy changes are the amount of energy that is released or absorbed by the system during these changes. I should say how much potential energy is released from the system or absorbed by the system. So when you have reactions that release a lot of heat, such as combustion, the enthalpy change for that is going to be negative and is releasing heat to the environment. And I'll go into that more specifically. You're going to hear the term system and surroundings a lot. I mean, technically, system is just any part of the universe that you're observing at a particular time. And the surroundings is everything else. And we do that because it helps us talk about energy transfers a bit with a bit simpler language. We're all aware of the law of conservation of energy, which says that in total, in the universe, energy is neither created nor destroyed in these chemical processes. So what we're really talking about is energy going from one part of the universe to another. But sometimes we only care about that one part of the universe, like a chemical reaction. So for a chemical reaction, it might release a bunch of heat energy. So we could say that the substances in that reaction afterwards have less energy than they started with. But total, the universe, the amount of energy hasn't changed. So even though during this topic we're going to talk about energy being lost and released and absorbed, it's just kind of a distinction to remind you that overall the energy is being conserved. So before we get into the actual equation, if we're going to talk about calorimetry, I like to use the analogy of an ATM. And I do that because when we talk about enthalpy, we cannot measure enthalpy directly. And I equate that to sort of, if you were talking about like ABN AMRO, the bank, or ING, at any one given time, there's not really any way to know the exact total net amount of euros or dollars that those places are worth. There's just too much money in those banks, and there's always money coming in and out. And so actually trying to figure out how much total money is in one of those massive banks is essentially impossible. But what's pretty easy to measure is a given transfer of money. So like if you have a bank account at ABN AMRO and you go to the ATM and you take out 100 euros, then if you get that ticket, your little receipt, it's going to tell you minus 100 euros from your account. And so it's easy to know the change in money for the bank, that when I take out 100 euros, I know that there's now 100 euros less at ABN AMRO. If I put 100 euros in, I know that there's now 100 euros more at ABN AMRO. The total money is almost impossible to measure, but the small transfers are what's easy to measure. The energy transfers can be measured. Another reason why I like this analogy is that it fits pretty well with the signs, the negative and the positive, that you're going to use with enthalpy changes. So remember, enthalpy is stored energy. Kind of in this analogy equal to the stored money that's in the bank. So if there's stored money in the bank and then you go and you take money out, in terms of the amount of money that ABN AMRO has, they just lost money, right? Money was released from the stored bank account. So when money is released to the surroundings, i.e. you and your wallet, the bank account loses money. And so therefore, you'd see a change in stored money is negative. Okay. So in the same way, when we're going to do reactions that release energy to the surroundings, reactions like combustion that are very exothermic, they release heat energy to the surroundings. Those reactions are going to get negative delta H's. So negative delta H. Okay. So just like you'd get a negative change on your bank account, when you have a reaction that releases heat to the surroundings, the amount of stored energy after that reaction is less than it was before it, and that's why the change is negative. Going back to the analogy, just real fast to wrap it up, it works the other way as well. If you were to put money in, the receipt would show that the amount of money in the account had increased. We'll just call it the stored money. All bold, which we don't need, so we're going to make that bold. Okay. So it's just the opposite. So when you do a transaction where you're putting money in, even though for you now have less money in your wallet, there's now more stored money. And so if we are looking at this, how much is stored, that's now increased. So that's a positive change. So that's a lot like an endothermic reaction. So this is the same as endothermic, and this one was the same as exothermic. Okay, so when energy is absorbed by a given process, afterwards there's more stored potential energy, and so therefore, if we're talking about change in just potential energy, that would be a positive change, and that's why the symbol is positive. And I apologize I'm drawing with my finger on the mouse pad, so hence the messy writing. Okay, so that's the ATM analogy. Remember that when stuff is released, there's a reason why it gets a negative sign. The stored energy has gone down, and when you put energy into something, the stored energy has gone up. So endothermic heat is absorbed by the system, resulting in an enthalpy increase. Delta H is positive. The change in enthalpy is positive. The classic sort of endothermic reaction to be aware of are decomposition reactions. When compounds break down into simpler compounds or into elements, there tends to be a net increase in enthalpy or absorption of enthalpy. Exothermic, these are much more common reactions, and heat is released by the system to the surroundings, and therefore the enthalpy, the stored energy of the compounds has decreased, so delta H is negative. The classic exothermic reactions the IB expects you to be aware of are combustion. That's a reaction where something reacts with oxygen and makes carbon dioxide and water. And neutralization, any like acid-base reaction that makes salt water, those are classic exothermic reactions. But most of the reactions that we talked about are somewhat exothermic. They're a lot more common, and we'll get to why down the road. So for you guys, there's really two kind of situations that you'll deal with in calorimetry, where you're actually trying to calculate how much energy was either released or absorbed by a given process. Probably the most common is, or one of the most common is the combustion. And so here's my flame. A lot of times they'll have you do a scenario where you're burning something beneath some water. And so what that means is that in this case, what you're burning is what we call the system. Okay? So in this case, whatever's in here is the system. Is the reaction. Okay? So the system is the reaction. This is the thing we're going to care about. Is this thing releasing energy, or is it absorbing energy? And I think we all know that if it's fire, it's very hot. So that's a sign that energy is being released as heat. The way that we're going to measure how much heat is being released is that we're going to essentially try to surround this reaction with water. So we're going to make the immediate surroundings for the reaction the water. So as heat is being released from the reaction, this combustion, that's what fire is, combustion. and it's releasing, it's a chemical reaction releasing heat energy. That heat energy is going to go into the water, and then we're going to be able to figure out how much energy has gone into the water because we're going to see the temperature rise on our thermometer. Okay. Obviously, there are some issues with this system, and we'll get to those down below, you can see. Okay, so in this case, we've got the system here, and the water is our surroundings. And so if we can measure the energy change of the surroundings, we can measure how much was released by the system. In the second case, both the system and the surroundings are in the same place. So this is a little bit trickier. So if you make a different color, if you have a reaction that happens inside aqueous solution, so this would be like that acid-base scenario. If you poured two solutions together and when they meet, they start to react and they release energy, then the reaction is happening right inside the water. And so as the heat is released from the reaction, it's in all directions going to be surrounded by the water. And again, temperature is going to go up. Okay. Now, both these examples are exothermic, so I talked about heat energy being released. It would work the same way, especially for the aqueous one, if you had endothermic. In that case, the arrows would go backwards from the water into the reaction. So as the reaction happens, they'd be absorbing heat out of the water, and you'd see the temperature in the thermometer go down. And we'll get to the equation and how to calculate this in just a second. As you can see, the most major flaw of any sort of calorimetry setup, especially ones that we can pull off in our lab, is that there's going to be lots and lots of heat loss to the surroundings. Okay, so in theory, what we really want to happen here is we want all the energy from the reaction to go into the water, because then if we can measure that temperature change, we'll have a pretty accurate assessment of the heat released by the reaction. But because a lot of the heat isn't, well, especially with this kind, with the combustion, because it's outside of the water container, a lot of the heat is just going to be lost, right? It's never even going to make it into the water. Some of the heat's going to go into this beaker or this container, whatever it is, this little metal cup. Some of it's even going to go into the thermometer. And then some of the heat that goes into the water is actually going to leave the water. As the water gets hotter than the room, then there's going to be even more heat loss. So the classic sort of experimental error, systematic error to talk about if you're doing an IB question on this topic is heat loss to the surroundings. And they do underline to the surroundings. Again, it's that system surroundings thing. So it's very common for that to take place. In this other kind, you can still have some heat loss to the surroundings, but it's a little bit more minimized because the reaction really is surrounded by the water directly. So maybe the thermometer absorbs a bit that you don't want it to. Maybe the glass beaker or the metal cup that it's in absorbs a little bit. Maybe there's a little bit of heat loss from the water. So you could still say in this example that heat loss to the surroundings is the major source of error, major systematic error, why your enthalpy change would be smaller than the literature value. But it's especially prevalent in this combustion example. A couple other ones just to be aware of while we're making a list is in the case of these combustion ones, incomplete combustion. So a lot of times if you're burning a fuel, if it's not in a nice efficient setup like a Bunsen burner that really mixes in a lot of oxygen, it's very common that not all of the fuel undergoes complete combustion. That means you're making some carbon monoxide or some smoke or some soot with this carbon solid, and that means less energy is released. Again, it's going to make the change in enthalpy smaller than you'd expect. You can also just have incomplete other reactions. Incomplete reactions. So if you're mixing things over here, maybe not everything reacts immediately, and as it takes time, you're back to losing some heat to the surroundings, and again, that's going to be an issue that makes delta H values smaller than literature values. Okay, So the actual way it gets calculated is with this equation, which is in your data booklet in the first table. So a calorimeter essentially surrounds a reaction with water. And so the assumption is that the heat absorbed by the water is the same as the heat lost by the reaction. Or flip that. You could say the heat lost by the water is the same as the heat absorbed by the reaction if it was an endothermic reaction. So here's what you need to do to calculate this amount of heat that's being gained or lost by the water. You need to know how much water you're heating up. That's M, the mass of water. You need to know the change in temperature of the water. That's pretty easy, and that should be in Kelvin, although it can be in degrees Celsius because when it's a change, it actually doesn't matter if it's degrees Celsius or Kelvin. And the last value is this thing called C, or lowercase c, specific heat capacity of water. It has the units of joules, which is energy, per gram per Kelvin. So it tells you how much energy does it take to heat up 1 gram of water by 1 Kelvin, or 1 degree Celsius. For water, this value is, I'm going to put it over here. So C is 4.18 joules per gram per Kelvin. So to heat up 1 gram of water by 1 Kelvin, or 1 degree Celsius, you need to give it 4.18 joules. It's the same number. Do that, work around, there we go. It's the same number if you do it in kilojoules and kilograms. So to heat up a kilogram of water, you need to provide 4.18 kilojoules of energy. So it can be done in either unit, so long as they're either both regular or they're both kilo. This is how much energy it takes to heat up water. It's a fairly high value if you think about how much energy it takes to boil water. It takes a really long time to get water up to that boiling temperature. But it takes the metal very little time to get very, very hot if you have water in like a kettle or a pot. So metal has a relatively low specific heat capacity because it's a very good conductor of heat. Water has a very high specific heat capacity at 4.18. So if you know the mass of water, the C value, which is a constant, which is in the data booklet, and you know the change in temperature of your water, you plug those into this equation and you'll know how much heat was absorbed or lost from the water. So if the water itself is absorbing energy, so if there's an exothermic reaction happening, then the water is going to get hotter. So with exothermic, the water gets hotter, temperature is positive, temperature change is positive, and Q is positive. So with exothermic reactions, then Q is positive. And if it's an endothermic reaction, then Q is negative. Because if it's endothermic, then the water is losing energy to the reaction. The reaction is absorbing it. And so for water, it's losing heat, and therefore the Q ends up being negative. So normally we're going to see exothermic reactions. You should usually be used to Q being a positive value when it's a positive delta T, but it's not impossible for them to give you an endothermic reaction. Just as a note, just so that we're aware this is a possibility. Sometimes, if you want to be a bit more accurate, and Ivy will give you a problem like this, they take away the MC and they just give you a C. So M times C together equals C. It's something called the heat capacity, and essentially it takes into account the total mass and specific heat capacities involved in the whole calorimeter. So if you look back here, rather than just measuring the mass of this water here, it'd be like figuring out how heavy the beaker is, how much water you have, how much the thermometer weighs, and the individual specific heat capacities of each substance, like the glass of the beaker and the glass of the thermometer, and then the water itself, and sort of averaging all those out and combining it together into one big value called C for that whole calorimeter. So now you don't have to weigh the water. It's already been weighed. You don't need to do any of those other things. So heat capacity is not like a constant for water. Heat capacity is specific to each calorimeter. Okay, so this is not anything you would ever be expected to sort of know a value for. But if they gave you a problem and they brought up this big C and you were kind of looking around for, well, where's the MC? Essentially, they've replaced MC with big C for this specific container. To turn Q into enthalpy change, which is really usually what you're going for, delta H, we need to do two things. We need to figure out the direction of the heat transfer, which we've kind of already done in our initial calculation. Is the value of Q positive or negative? Has the water absorbed heat or lost heat? And the other thing that we care about is how many moles of limiting reactant got used in this reaction. That's important because if I burn, 1 gram of fuel versus burning 100 grams of fuel, well, obviously burning 100 grams of fuel is going to give out a lot more energy. So usually we don't care just about like the total heat. We usually care about the amount of energy per mole that gets released, because that's what tells us a little bit more about that given reaction. Is it a reaction that releases a lot of heat energy per mole, or does it release only a little bit of heat energy per mole? So again, just walking through it, since water is normally the direct surroundings of our reaction, the sign on the enthalpy change is opposite to that of Q. So let me walk through that. If an exothermic reaction, we'll make it red, an exothermic reaction releases heat, right? So the reaction is actually losing energy. So the reaction or the system loses energy, right? So that's what happens when it releases it. Now it has less than before. So we'd call that a negative delta H. For the system, the molecules, the compounds, they now have less energy than they did at the beginning. That's why it's a negative delta H. But for the water, when you have a reaction that's releasing heat into water, well, if the water absorbs heat, there's going to be a positive change in temperature and therefore a positive Q value. So a negative delta H goes along with a positive Q value. That's just logically kind of how it works together. For endothermic, you have the opposite. So if a reaction absorbs heat and there's a positive change, in delta H, that's because the compounds or the system absorbs or gains energy. So if the compounds are gaining energy, now they have more stored energy than they did at the start, and therefore it's a positive change. In this case, where did that heat come from? That heat comes from the water. So for the water loses energy, and you end up with that negative Q value. So anyways, to summarize all that, if you want to calculate delta H, which I know you all want to calculate delta H right there, the change in enthalpy, then the real equation that you can break it down to is negative Q over N. Okay, so Q is the energy for the water, the energy either absorbed or lost by the water. The negative sign is what flips it so that we're now talking about the system instead of the water. And the N is the moles of our limiting reactant. Okay, so it's probably helpful to do an example. And I think this video is long enough, so we'll do some examples in class. But essentially, if you plug in a positive Q value here, the negative sign will make it negative, and so you'll end up with an exothermic negative H value here. If Q was negative from the water losing energy, it would end up having a positive value for endothermic reactions there. Last thing to summarize is just to show you what's called an enthalpy diagram or a potential energy diagram. These show you the progress of reactions. There should be labeled with H on this side, not delta H, but H, okay, on the y-axis. And essentially, what they just look like is this. In an exothermic reaction, the reactants and the products, here's the change in enthalpy. The change in enthalpy is a negative change. Afterwards, there is less stored energy than there was at the beginning. Okay, so what I've just drawn here, it looks like represents an exothermic process. Over here, this represents an endothermic process. Okay, so that represents the delta H, the change in enthalpy. So in this case, energy is absorbed, and therefore afterwards there's more energy in the system, more stored energy in the system. Okay, so this represents the change in enthalpy, the change in enthalpy. In this case, it's going down, right? That's why it's negative. In this case, it went up, which is why it's positive. Okay. Usually, you're going to connect these things with a little curve, like that. There's a reason for that bump. It's something called the activation energy, which we'll talk about a lot more as we go into kinetics. But essentially, for now, remember that exo involves a negative change in enthalpy, and that heat, to now turn it into a little sketch. This is not part of your normal enthalpy level diagrams. Where does all that energy go? It can't really be lost in the universe. Well, it leaves these particles, these system particles in our reaction, and it goes out here to the surroundings and makes the water get hotter. And that's why we see delta T going up. So we get big positive delta T's. So exothermic reactions feel warm, they feel hot, because the reactions are releasing energy. Endothermic reactions end up feeling quite cold, and they make temperature drop because they steal heat energy from the surroundings, and it gets locked away as stored potential energy. And so here's the surroundings, your water out here, and you're going to feel negative changes in temperature. So endothermic processes feel cold as they absorb heat from you and the surroundings.